year, we build a slightly different robot. As I mentioned, we only get 6 weeks in which to build it, although we can add a few tweaks after then, but we really can't do much major design after that. We have various electronics which distribute the power to the motors. Virtually all of our power comes from electronic DC motors. We do use a compressor and use compressed air for certain tasks, but the majority of our power is in motors. And then we have a set of computers, a control system to control all these motors and these pneumatics. The compressor, it is over here. It pumps up the air, and we store it at 120 psi in this tank or similar tanks. And then at 60 pounds per square inch, we power pistons, which we basically use whenever we need linear motion, such as just like there's a piston here which just kicks the frisbee out into the shooter, or we have 2-speed transmissions. So when we have a motor, normally it would spin very fast but very little power, well, not very little power, but very little torque. So it couldn't actually push the whole robot all that fast. So we use gearings similar to in a car to give it more torque and to allow it to push harder. But we have, similar to car, we also have multiple gears, and we use pneumatics to shift between those gears. We use a lot of motors, but we also use a lot of sensors to support our code and support our motors and give us more reliable results. Because without some of these sensors, we might be able to play, but we'd end up with frisbees being jammed all over the place. Some of the more common ones we use are encoders, which basically are rotational sensors. They tell you how many degrees it's turned since the start or whatever. We also use some things which basically detect magnets, and we place magnets somewhere, and then when, say, this goes up, that sensor and there's a magnet right in here somewhere. The sensor is right here and sees the magnet, and we can tell whether or not this has gone all the way up, and if it hasn't, then we're jammed. And then we can do something about it, whereas if we didn't, then it might go up partially and then try to continue and get even more jammed, and we'd have all sorts of issues.
Okay, so you say a little bit about how many parts there are in the robot, what the cost is, and how many days and how many people it takes to assemble it?
How many parts? This year was our most complicated robot. We're trying to simplify it, but we had on the order of what, 200 parts? Unique parts?
250.
250 unique parts? Or
it's between 200 and 250.
Okay, lots of parts. And we have a set of very generous manufacturing sponsors, which basically will make these sheet metal parts, or in some cases, they did the welding that you see here, and all this. We have a group of students who work very hard to get these sponsors involved and communicate with them as effectively as possible, and gives us a lot of experience with how you actually have to design things to be manufacturable rather than just designing however we feel like, such as it'd be impossible to actually make or very inconvenient to make. You said cost as well?
Cost?
And man hours. Okay, so cost. Last year we spent
$28,000 on 2 robots.
Yeah, $28,000 on 2 robots. Because normally we build 2 identical robots, because one of them we have to bag up and not touch until the competition. Because different teams have their competitions at slightly different times. Because there's a whole bunch of competitions, you can't have 70 regionals all in 1 week. So they space them out over the course of around 7 weeks. And so you have to bag up one robot, and that's when you use a competition, but we keep another one, we make another one, so that we can test things on it, make sure it won't break, and then we know what to expect to have to fix at competition. And during the season, in terms of amount of time, our most dedicated members tend to show up every day, and on the Friday evenings and on the weekend evenings, people will stay quite a while.
However long they feel like staying.
Yes, we've been getting more tools, learning how to use them. So this past year we got a set of sheet metal tools that we can use, and as well as a lathe. And we know how to use sheet metal tools for the most part. We're working on improving our use of them, and we're working on how to use the lathe as best as we can.
Block, and down here is a sim
that drives this shaft. And it would bring these Frisbees up around here. And I don't know, is this like the 10th iteration on this or
At
what?
least.
At least, okay. So,
I rebuilt this at least half a dozen times.
yeah, and right when it showed up, we got this metalworking equipment, so we're learning how to make it, how to use
All
it.
these gearboxes were made on those machines.
Yeah, made gearboxes and stuff. All this is done like, let's try this, and 2 or 3 students will work with a mentor on one part.